This very first lesson is going to be about solving systems of linear equations on the very basic level. So we're going to look at some examples that should be very familiar to you, and I'm just going to remind you of some techniques that you should have used at some point in your past. Here in part A, we have two equations and two unknowns. So we could graph this and we could look at the solution, or we can use substitution, or we can use elimination. So there's a variety of different ways we can use this. So I'm going to use elimination. So what I'm going to do is I'm going to multiply this first equation by -5. So I get negative 5x1 minus 5x2 equals negative 160. I'm going to leave the other equation alone. So 5x1 plus 10x2 equals 220. I'm going to add them together. So when I add them, my x1s go away, and then I get 5x2 equals 60. I get x2 equals 12. And then to find x1, I can plug back into either one of the equations. I'm going to take the first one. So I'm going to say x1 plus my x2 is 12 equals 32. So x1 equals 20. So again, this is called elimination. So my solution would be 20, 12. For this next one, I'm going to use a different method. Let's use substitution. So I'm going to take this first equation and I'm going to solve it for one of the variables. It's easier to solve for x1. So I'm going to say 44 minus 2x2. I'm going to use this. I'm going to plug it into x1 in my second equation. So I get 5 times 44 minus 2x2 plus 10x2 equals 220. And then distributing, I have 220 minus 10x2 plus 10x2 equals 220. Notice my 10x2's add to 0, and I get 220 equals 220. This is always true. It doesn't matter what x1 and x2 are, so the solution is all real numbers, or all ordered pairs. So I'm going to say all x1, x2, where x1 and x2 are real numbers. For part C, I'm going to do the same thing as the first one. So I'm going to multiply this top equation by -5. Negative 5x1 minus 10x2 equals 220. That should be a negative 220. And then I have 5x1 plus 10x2 equals 230. Those x1s go away. Oh, notice my x2s go away. So I have 0 on the left. And then I'll have a 10 on the right. This is never true for all x's and x1s, x2s you pick. This is not possible. So this is no solution. So this is 3 types of solutions we can get. We can get one solution, infinitely many solutions, or no solution. So graphically, what that might look like, notice in this first graph, there's this tiny little green and tiny little blue. Those are the 2 equations. So you can't really tell, but they are on the same line. So when you graph and they are a line on top of a line, that is infinitely many solutions. So I sometimes write infinitely many because they intersect at every single point. This is one solution because they intersect at one point, and this is no solution because they don't ever intersect. So just some terminology. This course is a lot of terminology, so you might want to make a sheet with all the different words. So we say something is inconsistent if it has no solution. We say that it is consistent if it does have a solution. If it has only one solution, we call it unique. All right, so that was just kind of a review of what, those are the only 3 possibilities you can have. One solution, no solution, or infinitely many solutions. Now we're going to get into the notation of linear algebra with a matrix. So an augmented matrix is a matrix that includes the right-hand side, so it includes those. This first column is the coefficients of the x1s. The second column are the coefficients of the x2s. And so here's my x2 column. And then here's my xn column. And this is I often put right-hand side, my right-hand side column. So again, the augmented matrix is different from a coefficient matrix in that it includes the right-hand side. Sometimes we put that little line there to emphasize it as augmented, but sometimes we don't. So just be aware of what kind of matrix, whether it's augmented or a coefficient matrix. So this first two examples here are convert the augmented matrix. So if we say, oh, it's augmented, maybe I'll put that little line there, back to a systems of equations. And looking at the matrix, you don't know what the variable names are. So we can use x1, x2, x3, we can use x, y, z, really use any. You tend to use the later end of the alphabet for variables and the beginning of the alphabet for constants. All right, so if I use x, y's, and z's, this first line would be x plus 2y minus 4z equals -1. The next line would be 4x plus 5y plus 3z equals 12. 3x minus y plus 6z equals 8. So that is this is the augmented matrix for this system of equations. This next one, try to do on your own. I'll just put the answer down. So which system is more difficult to solve? If you look at the second one, I can just take that last equation and say z equals 1. Then I can plug z equals 1 to the previous one. I get y minus 2 equals -1. So I get y equals 1, and so on. So this is called back substitution. In this first system of equations up here, I don't have that flexibility. So the second one is much easier to solve. So in the first three examples we saw, we used elimination and substitution. When you have it represented as a matrix, there are what we call elementary row operations. In other words, things that you are legally allowed to do to the matrix that is really modeling elimination. So here are the three things that you're allowed to do. You can interchange rows. In other words, it doesn't matter which equation you write first. You can multiply a row by a non-zero constant. That is the same as like in that first system I multiplied by -5. It didn't change the system, so you can multiply by a non-zero constant. And then you can replace a row by the sum of itself and a multiple of another. When I added the two equations in that first example, that's what I was doing. So I'm going to apply elementary row operations to this augmented system. You can put those dots there to emphasize augmented, and manipulate it into a triangular shape. So you may not know what that means at this point. I'm going to call this row 1, row 2, row 3. And my goal is going to be to get it in triangular form. So that means I want to get these to be zeros. So I'm going to take row 2, and I'm going to have that equal to the current row 2 minus 4 row 1. I'm going to take my current row 3, I'm going to say row 3 equals row 3 minus 3 row 1. So just to keep in mind that this 3 comes from that 3, and that 4 comes from that 4. All right, so when I do this, my first row doesn't change at all. So 1, 2, -4, -1. Row 2 is going to be the current row 2 value, which is a 4, minus 4 times my row 1 value. My current row 2 is 5 minus 4 times 2. And then 3 minus 4 times -4. 12 minus 4 times -1. And then similar with the row 3, I'm just going to say my current row 3, which is 3 minus 3 row 1, -1 minus 3 times 2, 6 minus 3 times -4, and then 8 minus 3 times -1. So this is what we get when we simplify that arithmetic. Now I want to zero out this, so I'm going to make row 3 equal to row 3 minus 7/3 row 2. And that 7/3 comes from that ratio. And when you do that, the first row is going to stay the same. Second row will stay the same. And my third row will be 0, 0, negative 79 over 3, and negative 79 over 3. So this is in triangular form because these below the diagonal, so if this is the diagonal, below the diagonal is all zeros. So I just want to point out that we can keep applying row operations until the leading entry of every row is a 1, and the leading one is the only non-zero. So what that means is we can keep row reducing, so don't mess with the zeros below. You can make it so that all the diagonal entries are 1, and you can also modify it so that you have zeros above all your leading ones. And because this is augmented, you'd still have some values out here. So we will practice more of this row reduction in class. So last thing I want to point out is, why this process works. Just like with using elimination, we can use these manipulation techniques. We call them elementary row operations. And we say that two matrices are row equivalent if you can reach one, get one from one to the other by using these elementary row operations. And then if two are row equivalent, then they have the same solution. So in other words, when you apply these elementary row operations, you're not changing the solution.